lecture of analog and digital communication. This is today's our topic is various form of differential pulse code modulation. We have already covered some form of differential pulse code modulation. Now in today's lecture we will see the form of a delta modulation, that is adaptive delta modulation. So in earlier lecture we have seen that we are interested in transmitting as low bits as required for the voice signal. So what we are doing is we can either we we have seen that by knowing the previous sample value and the present sample value we can predict the future value of the sample. So there are various methods where we are transmitting the difference of signal. One such form of a modulation is called differential pulse code modulation, where we are transmitting the difference of the kth sample and its predicted value. The predicted value will be given by the predictor, which is nothing but a transverse filter having some delays. So the difference between mk and mqk is dk, and which is quantized and transmitted to the channel. So this is the DPCM transmitter, and at the receiver we are receiving the difference signal, and by knowing the previous sample value and difference value, by adding these two we can get the output, that is MQK. So this is the way the DPCM transmitter and receiver work. But still the channel bandwidth or bit rate required will be less than the PCM, but still it is somewhat higher. So one advanced version of DPCM is called 1 bit DPCM, or simply a delta modulation. So this is simple a transmitter and receiver of delta modulation. Since this is in delta modulation, we are sampling our signal at very high rate than the Nyquist rate, at least 5 or 6 times the Nyquist rate. So since the sampling rate is high, the samples are near to each other, so it will have a high correlation. So the correlation between samples are high. Since the correlation are high, the difference between the samples will be very small. So we can encode that difference between sample by single bit. Hence this is called as 1 bit DPCM. So we can replace the predictor by delay, 1 bit delay, and we'll take the difference of mk and its previous sample version, that is mk minus 1. That will be the difference signal, and that will be quantized and that will be transmitted over channel. So this will be the simplified delta modulation block diagram. Still we have done the mathematical analysis, and we have found out that by simply having an integrator instead of the predictor, we can have the simple arrangement of a delta modulator. So here the signal so what is the reason to use the delta modulation? So we have observed in the PCM that it transmits all the bits which are used to code a sample. Hence the signaling rate and the transmission channel bandwidth are quite large in the PCM. To overcome this problem, delta modulation is used. In the question is how it will work. What is the working principle behind delta modulation? So delta modulation transmit only 1 bit per sample. Here the present sample value is compared with the previous sample value, and these results whether the amplitude is increase or decrease, and that will be transmitted. Input signal is approximated to step signal by delta modulator. This step size is fixed. So you can see here we are having the incoming signal MT and the predicted version of signal, that is MQT. These two are compared, and depending upon the difference, if this difference signal is positive, this amplitude so if the difference is positive, it can be either positive or negative. If the difference is positive, then approximated signal is increment by one step. The positive step is here is delta positive step is E, or simply it will increment or decrement by one step, that is delta. If the difference is negative, then approximated signal is reduced by delta. So by knowing only plus or minus whether signal, by comparing this, and if signal level is positive or negative, will denote this by 1 or 0. When the step is reduced, 0 is transmitted, and if step is increased, 1 is transmitted. Hence for each sample only one binary bit is transmitted. So it will produce the staircase at the output. So the transmitted signal is the difference signal, so it will be a impulse signal. If the difference is negative, -1 is transmitted, or simply this represent -1, or you can say 0. And if the difference is positive, then +1 or simply a 1 is transmitted. At the receiver, we are receiving the signal, and that signal is amplified and given to the integrator, and that will produce the staircase, because our input is the impulses. The integration of impulse is step pulse. So the output of integrator is staircase, or simply a step kind of a response corresponding to each pulse, each impulse, and it is passing through the low pass filter. So this will be a continuous response like a staircase response. So you can see here our signal is empty, and this is the output of our integrator and low pass filter. So these two are compared at each and every sampling instant. So you can see that if the difference between MT and MQT is positive, that is MT minus MQT is positive, then it will transmit 1, and if it is negative like this, then it will transmit -1 or 0. So this is the signaling it will transmit, and the error is shown here, that is difference of the original signal MT and the MQT. You can see here when the difference is xt minus x, this is our input signal, and this is the approximated signal. If difference is positive, then 1 is transmitted. If difference is negative, then 0 is transmitted. So the advantage of PCM, or advantage of delta modulator, is the delta modulation transmit only one bit for one sample. Therefore, the signaling rate and transmission channel bandwidth is quite small for the delta modulation compared to the PCM. The second advantage is the transmitter and receiver implementation is very much simple. So there is no analog or digital converter required in delta modulation. Directly signals are compared. You can say directly MT and MQT are compared. It is not analog to digitally transmitted. There are two drawbacks. Advantage we have seen. Advantage is delta modulation transmit only one bit per sample. So no signaling rate and transmission channel bandwidth is, so transmission channel bandwidth is very small compared to PCM. It will require very much less bits to transmit information, and the transmitter and receiver implementation is very easy. So these are the disadvantage, and the disadvantages are the delta modulation has, it will produce two type of noise. One is called slope overload noise, and second one is called granular or ideal noise. In slope overload noise, so this distortion arises because the large dynamic range of input signal. So as you can see from the figure, the rate of rise of input signal xt, this is our input signal xt, cannot be approximated. so this rate of increase is so high, or simply you can say this slope is very much high, so that our staircase approximation is not able to catch up that signal. So the rise of input signal xt is so high that the staircase signal cannot approximate it. The step size, this is the step size, the step size delta become too small for the staircase type of a signal to follow the step segment. Hence there is a large error between the staircase approximated signal and original input signal xt. The error or noise, this kind of error or noise is called as slope overload distortion, and the noise corresponding to the slope over distortion is called slope overload noise. So it will occur, once again it will occur whenever there will be very large slope, and this increment or change in height is fixed, the step size is fixed, so it will take much more time to it will at each and every sample instant, sample instant it will increment by a fixed size, the step size increase by fixed size, so it will not there will be large difference between the actual signal and the approximated signal, and this is called slope overload distortion. The second type of sorry, now to reduce this error, that is slope overload distortion, the step size must be increased when slope of signal xt is high. Since the step size of delta modulator remains fixed, its maximum or minimum slope occurs along the straight line. Therefore, it is also known as linear delta modulator, LDM. The second type of noise is called granular noise, which is shown in this figure. So granular noise occurs when the step size is too large compared to small variation in input signal. This means for very small variation in the input signal, like shown in this figure, where the input signal variation is very small or it is almost constant, the staircase signal, this means that for very small variation in the input signal, the staircase signal is changed by large amount, that is delta, because of large delta or large step size. So this figure shows that when the input signal is almost flat, the staircase keeps on oscillating plus or minus delta around the signal. The error between the input and approximated signal is called granular noise. The solution of this problem is to make step size small. Therefore, a larger step size is needed or required to accommodate wide range of input signal or to reduce the slope overload distortion. So the solution of slope overload distortion is we require large step size to accommodate large dynamic range, and to reduce granular noise we require small steps to reduce granular noise. So the same thing is done by adaptive delta modulation. That will be the modification in the delta modulation that we'll see right now. So before this, how to reduce this delta modulation, that we have seen that by increasing the step size we can decrease the delta modulation, but we have to find out the maximum slope that can be allowed, or that can be allowed, or that we have to find the optimum value of this step size E, which will give us minimum slope overload as well as which will give minimum overall noise or minimum granular noise. If you will increase slope this step very much large, then granular noise will increase, and if it is very small, then slope overload will increase. So we have to choose the optimum value of E such a way that the best compromise between the slope overload and granular noise will be there. So optimum E will depend upon Fs, that is called sampling frequency, and the second thing is it will also depend on nature of the signal. So the slope overload occurs when our signal MQT cannot follow MT. During this sampling interval, that is TS, MQT is capable of changing by sigma, that is sigma, or you can say delta. It can change either plus delta plus height of the signal or less plus or minus delta. Hence the maximum slope that MQT follows is maximum slope that MQT follow is E by TS, or simply that will be 1 upon TS is Fs, so it will be 1 upon TS, or simply E into Fs, where Fs is the sampling frequency. Hence, no slope overload occurs if the magnitude of slope, that is magnitude of mt by dmt by dt, that is the differential of mt, that is called as slope. So the magnitude of slope of signal mt is less than E into Fs, then no slope overload will happen. So let us consider the case of tone modulation, where we are using only a sinusoidal signal. So mt is equal to a cos omega t. We are using a pure sinusoidal signal, that's why this is called as a tone modulation. Now when we will take the differentiation, that is m dash t, then it will be a omega cos omega, a omega sin omega t, and if you will take the magnitude, then it will be only omega a. So the magnitude of slope, or magnitude of our signal, the slope of signal, the maximum slope of signal is omega a, and from the previous condition, so this should be less than E into Fs. By readjusting this, it will give the maximum amplitude that can be permitted will be equal to E into Fs divided by omega. So the slope amplitude of the overload amplitude of the modulating signal is inversely proportional to the frequency omega. For higher modulating frequency, the overload occur for the smaller amplitude. For voice signal which contains all frequency component up to 4 kHz, calculating A max by using omega, so omega is equal to, we are considering only 4 kHz signal, that will be maximum frequency is 4 kHz, or omega is 2 pi f, or 2 pi into 4000. This will give the conservative value. It has been shown by scientist called Jaeger that the maximum, that is A maximum or maximum amplitude A max for voice signal can be calculated by reference frequency 800. So our omega r, that is reference frequency, is, instead of this omega we will use omega r for voice signal, that will be 2 pi into 800. Thus the maximum voice signal amplitude A max that can be used without causing slope overload in delta modulation is same as the maximum amplitude of sinusoidal signal of reference frequency, that is 800 Hz, that can be used without causing slope overload in the same system. So we are using reference frequency is equal to 800 megahertz, whatever the amplitude of 800 megahertz, 800 kilohertz signal will be there, that will be our reference, and that will be used as a, so if there will be maximum amplitude signal variation in 8 megahertz, 8 kilohertz, 800 kilohertz, then that will be 800 hertz, then that will be the variation in the there will be no variation in the slope overload. Now we have already seen, to overcome this these two type of distortion, a large step size is required to accommodate wide dynamic range of input signal, or to remove the slope overload distortion, and small steps are required to reduce the granular noise. So adaptive delta modulator will be used. So this is the transmitter of adaptive delta modulation, which will be same as the earlier one, that only one thing is added here. So the question is, why we are using adaptive delta modulation? So the answer is to overcome the quantization error due to slope overload and granular noise. The step size is made adaptive to the variation. Particularly if a steep segment of input signal xt is there, that is which will have a large slope, then the step size is increased. Also, if the input signal is varying slowly which will be a very the constant one, the variation of the signal is very slow, the step size is reduced. Then this kind of method is called adaptive delta modulation. The adaptive delta modulation can take continuous change in step size or decrease the change in step size. This particular figure shows the transmitter of the adaptive delta modulation. The logic level for step size the logic level for step size control is added in this diagram. If you compare this diagram with the previous diagram, only this block is added, that is logic for the step size control. The step size increases or decreases according to the specified rule depending on 1 bit quantizer output. So this will depend upon output of this 1 bit quantizer output. As an example, if 1 bit quantizer output is high, if it is 1, then step size may be double for the next sample. If 1 bit quantizer output is low, after this difference, if this output is low, then step size may be reduced by 1 step. So you can see here this logic is implemented here. You can see this is our signal ut, that will be the input signal, and this is the approximated signal, that is xt. Xt is approximated signal, the xt is our input signal and ut is our approximated signal. So when it will take the difference, that is xt minus ut, if the difference is positive, then that will approximated by 1 and there will be increment, one step size increment. Once again, let us take at this point. So there are two increment here. Let's compare here. The signal xt is once again positive compared to ut, so it will take now 2 increase in, there will be this delta 2 is larger than delta 1, or simply it will be 2 times the delta 1. So there will be step increase in, the step size is increased compared to previous one. In earlier case, that in delta modulation this step size was fixed. Here the step size is varying according to the slope of the signal. Once again you can see that once again it will be compared at this point, and this will be negative. This is xt minus ut is positive, hence once again the step size is increased and this delta 3 is greater than delta 2. So this way the step size is increasing and the slope overload distortion will not take place. Similarly, when you see that when the signal is somewhat constant, where its amplitude level is not changing very large, or simply you can say the slope is very small, then the size of this pulses are decreasing, or height of this pulse are decreasing. So this will reduce the granular noise. So this way adaptive delta modulation will work. In the receiver part, we are having, there are two portions. The first portion produces the step size for each incoming bit. This is the first portion and this is the second portion. So the first portion produces the step size from each incoming bit. Exactly the same process is followed as there in a transmitter. The previous input and present input decide the step size. It is then applied to the accumulator. This is our accumulator section. So this accumulator section builds up the staircase waveform. The low pass filter then smoothes the staircase waveform and reconstruct the original signal. Next is advantage and disadvantage of adaptive delta modulation. So adaptive delta modulation has certain advantage and disadvantage over the delta modulation. The first one is the signal to noise ratio become better than, sorry, wait. The signal to noise ratio becomes better than the ordinary delta modulation. Why? Because the overall noise, that is the slope overload noise and granular noise, are decreasing and the signal amplitude is constant. So signal, since denominator is decreasing, signal amplitude is constant, so signal to noise ratio, noise is decreasing, so signal to noise ratio will improve. So the signal to noise ratio become better than the ordinary delta modulation because of reduction in slope overload distortion and granular noise. The second advantage is because of variable step size, the dynamic range of ADM, that is adaptive delta modulation, is wider than the simple delta modulation. The third advantage is the utilization of bandwidth is better than delta modulation. The fourth one is only 1 bit per sample is required. That was also in case of delta modulation, but this is not advantage, these are equal. Overall advantage compared to PCM, you can say that the only 1 bits per samples are required and the transmitter and receiver are simple. So implementation of transmitter and receiver circuitry is simple. This is the comparison of all the modulation scheme we have seen in this chapter. This is PCM, delta modulation, adaptive delta modulation, and DPCM. So it will start with the number of bit. We have seen in the PCM that for each sample number of bits are fixed. So if the number of bits are 4, then each sample bit or each sample is encoded with 4 bit. In delta modulation we are using only single bit per sample. Same way for the adaptive delta modulation. And for differential pulse code modulation, that is DPCM, the bit rate is smaller than the PCM, but it will be larger than ADM and DM. Second is level and step size. The number of level in PCM, the number of level depends on the number of bits. Level size is fixed. We have seen the level is given by, or simply the delta is given by 2MP by L. So L is the level, that will be 2 raised to n. L is equal to 2 raised to n. So the number of level depends on the number of bit. L is equal to 2 raised to n. If it is equal to n is equal to 4, then number of levels are 16. If it is equal to 2, then number of levels are 4. L is equal to 2 raised to n. So the number of levels depends on number of bits. So once the number of bit is fixed, the level size is kept fixed. In delta modulation, step size is fixed and cannot be varied. Because of that, we are having two distortion, that is slope overload and granular, and this will be overcome in adaptive delta modulation. So according to the signal, the step size will vary in adaptive delta modulation, and in DPCM also the step size are fixed. The errors in different modulation scheme are, in PCM we are having a quantization error, that will be del V square by 12. So the quantization error, which will del V square by 12, so that will depend upon levels used. Del V square by 12, well, del is the height of sample, so it will depend upon number of level used in PCM. And in slope, this delta modulation, we are having two error or two distortion, that is slope overload distortion and granular noise. In adaptive delta modulation, once again we are having a quantization noise, but no other errors are there. In differential pulse code modulation also we are having a slope overload distortion and quantization noise. The transmission bandwidth, this is the most important thing. The highest bandwidth are required in PCM because each sample are sample encoded with the predefined number of bit. Let us take if it is 4, then each sample are encoded with 4 bit. So the highest bandwidth is required since the number of bits are high. In delta modulation only one bit is used, so the lowest bandwidth is required in delta modulation. In adaptive delta modulation also we are transmitting only one bit, so delta modulation and adaptive delta modulation both will have a lowest bandwidth, and the bandwidth in DPCM is somewhat less than PCM but higher than delta modulation and adaptive delta modulation. In pulse code modulation there is no feedback in the transmitter or receiver. In all other modulation the feedback will exist. The system in PCM is complex one. It involves quantizer, then encoder, and then quantizer. Encode. First of all, there will be low pass filter, then there will be this quantizer, and that will follow by the uh, quantizer and encoder that will be amplified and that will be transmitted. In delta modulation circuit is simple. It will have one predictor and only one summer circuit, sum and difference. So and that will be in a feedback. So the circuit is delta modulation. We are having only comparator and integrator. Same thing will be there for adaptive delta modulation, and in differential pulse code modulation we are having a predictor and comparator, that is different circuit. So the complexity of implementation will be simple in delta modulation, adaptive delta modulation and DPCM, but that will be somewhat complex in a pulse code modulation. So these are the comparison of PCM, DM, ADM and DPCM. The next thing, the last topic of our this chapter in our syllabus is T1 carrier system. So what is this T1 carrier system? We already know different kind of multiplexing. When we are having more large number of input and we are having a less number of channels, or we want to utilize the channels effectively, then we are using multiplexing. So many number of inputs can be taken and the resources can be shared in this channel. So there are two schemes. One is called TDM, that is time division multiplexing, where we are sharing the time, and in frequency division the second scheme is called frequency division multiplexing. In frequency division multiplexing we are allotting the different frequency to each user. Let us take I am having a 100 megahertz frequency band. Then if each user are given a 10 megahertz frequency, then 10 such user can be accommodated. So this 10 megahertz of frequency is dedicated to each user, whether they will use or they will not use. The 10 megahertz frequency is allotted. So if they not use the 10 megahertz frequency, then that frequency cannot be, it is not used by other one, and that will be lost in the system. So that is FDM, and this is also called FDM is you can say it is an analog kind of a system. And in TDM we are having a we are setting the time division multiplexing. So the channel is fixed, different time durations are given to each channel, and that channel or each user, during that time only that person or that channel, the person is able to transmit during that time only in the channel. That is called TDM. So a PCM TDM system is a T1 carrier system. The system which uses pulse code modulation and which uses TDM system, that is time division multiplexing system, is T1 carrier system. So when a large number of PCM signal are to be transmitted over a common channel, multiplexing of this PCM signal is required. So the basic time division multiplexing scheme called the T1 digital system or T1 carrier system is used. This system is used to convey multiple signal over telephone line using wideband coaxial cable. So the working principle or the diagram of T1 carrier system is shown here. The working operation of this T1 carrier system can be explained as, so you can see is this system has designed to accommodate 24 voice channel. You can see here it is written channel, and such 24 channels are there. Each signal is band limited to 3.3 kilohertz. 24 channel, and each signal is band limited to 3.3 kilohertz, and the sampling rate, so the maximum bandwidth is 3.3 kilohertz for each signal. So our Nyquist rate should be twice the maximum frequency, that will be equal to 3.3 into 2, so that will be 6.6. But we are oversampling to the Nyquist frequency, and we are using 8 kilohertz standard sampling rate. This is the higher than the Nyquist rate. The sampling is done by this switch. This is not a hardware switch. This is a electronic switch whose sampling period or whose switching time is very much small, and switching frequency is very much high. So this is also called as commutator switch. So this is our commutator switch 1, and this is our commutator switch, or this will be called decommutator switch. So this is switch 1 and this is switch 2. Now this voice from, or the signal from this 24 voice channel are selected one by one. Depending on this, each voice channels are given a time period, and that will be decided by this commutator switch. So these signals are selected one by one and connected to PCM transmitter by the commutator switch, this commutator switch SW1. Now each signal sampled, this will have the signal, and the sample is taken by this. So each sample signal is then applied to the PCM transmitter. So PCM transmitter will have quantizer and encoder. So this sample signal are encoded by this coder, and that will be compressed by this digital signal processor. So each sample is then applied to PCM transmitter, which will quantize and code, which will convert into digital signal by process of analog to digital conversion, and the compressing of signal will take place here, or simply a compounding process as explained earlier. Next, the signal is transmitted over a transmission medium, that will be a wideband coaxial cable. So, and during the transmission, periodically after every 6,000 feet, the this T1 carrier signal is regenerated by amplifier, which is called as regenerative repeater. So regenerative repeater eliminate the distortion introduced by channel and remove the superimposed noise and regenerate a clean signal at their output. It will accept the input pulse or input signal, and it will regenerate it by removing all the noise, and so this ensures that the received signal is free from the distortion and noise. At the receiver side, this is the transmitter section and this will be the receiver section. At the receiver side, the reverse process will be followed. So first, the signal which is being compressed here along the transmitter, that signal will be decompressed here. So decompounding here, compounding is done, and or simply compress is done, and here decompress. So compounding process will be there. The decompressed signal is given to decoder, and that decoder, the PCM receiver output is connected to, so this will be decoded, and this output is connected to different low pass filter via a decommutator switch. This is our decommutator switch SW2. The synchronization between transmitter and receiver commutator, that is SW1 and SW2, these two switch, is essential in order to ensure the proper communication channel. Now there are various terms related to this T1 carrier system. This carrier system was used in America, and Europe there is other system that is called DS system, but in our syllabus we are having only T system, and this particular system is called T1 carrier system, while in Europe and rest of the world the system used is called DS1, digital signaling level 1 or digital signaling level 2 kind of a system. Now there are important terms related to this carrier system, so we'll see one by one. First of all is called beat per frame. What will be the beat per frame, and what is this frame? The commutator sweep continuously from switch 1 or the channel 1 to channel, you can say we are having many channels, 24 such channels are there. So this commutator switch is swept from 1 to 24 and once again set back to 24 channel S24 at the rate of 8000 sample per second. 8000 revolution per second. In 1 second this switch will take 8000 switching or 8000 samples. 8000 revolution per second. The switching rate will be 8000 revolution per second. So this will generate 8000 sample per second for each signal. 8000 sample per second for each signal, and each sample is encoded into 8-bit digital word. Each sample is encoded to 8-bit word. So the digital signal generated during one complete revolution of commutator is called one frame. So one frame consists of this 24 channel. One revolution, in one revolution we are having 24 channel. So one frame is equal to one revolution, that will be equal to 24 channel, and each this 24 sample will be encoded by 8 bit. So 24 cross 8. So per frame there will be 24 cross 8, that will be 192 bit. So one frame of T1 carrier, you can see here. So you can see here each channel is encoded by 8 bit. Each sample is encoded by 8 bit. This will be the coder output. This is the framing or T1 signaling format. So you can see. So one frame of T1 carrier system is shown here. Each voice signal from first channel to 24 channel is encoded into 8 bit. One frame corresponds to the time corresponding to transmission of each signal once. Hence one frame corresponds to one revolution of commutator, or one frame is equal to one revolution is equal to 24 channel. So it requires 192 bit for one frame. Now one more bit is added. You can see the one bit which is denoted by F, that is framing bit. So as discussed earlier, the synchronization between the transmitter and receiver commutator is essential. Without such synchronization, the receiver cannot know which bit corresponds to which of the original signal. To provide such synchronization, an extra bit is transmitted preceding the 192 bits. So previous to each frame, one F bit is transmitted. This bit is called the frame synchronization bit, F. Thus one frame synchronizing bit is transmitted per frame. This makes total number of bits equal to 192 plus 1, that will be equal to 193. 192 we got from 24 channel, and each channel or each sample is encoded by n bit. So 24 cross 8, that will be equal to 192, and plus this one framing bit, so 193 bits are transmitted per frame. And the time slot for 24 signal and extra frame synchronizing bit is shown here. The next important thing is one more thing is the for synchronization 12 successive F slot are used to transmit a 12 bit code. So every 13 frame the code, one synchronization code is transmitted, and the code is 1101 1100 1000. So these 12 bit codes are transmitted. This code is transmitted repeatedly once every 12 frame. So once these 12 frames are passed, this code, that is 1101 1100 1000, is transmitted after every 12 frame, and it is used at the receiver to obtain synchronization. So fixed bit frames are or fixed bits are transmitted so that there will be synchronization at the receiver, and the bits are 1101 1100 1000. So these 12 bits are transmitted after every 12 frame. So 13 frames will always be this one. So the next important thing is bit rate. What will be the bit rate of T1 carrier system, or what? Okay. So in T1 carrier system, before this, the bit rate is nothing but the number of bits transmitted by system per second. Number of bits transmitted per second. Bit per second. So in T1 carrier system, each signal is sampled at 8000 times per second. Therefore in one frame, that is the one revolution of commutator, so that will be equal to 1 divided by 8000, because each signal is sampled 8000 times per second. 8000 times are sampled. So one sample corresponds to, or one frame corresponds to 125 microsecond. That is 1 divided by 8000, that will be corresponds to 125 microsecond. But one frame is having only 193 bit. One frame is having only 193 bit. You can see here each frame takes 125 microsecond, because sampling rate is 8000 per second. So each frame is having 193 bits. So 193 bits are transmitted in 125 microsecond. So the number of bit in 1 second will be, in 125 microsecond 193 bit are transmitted. So in 1 second how many bits are transmitted? That will be 193 divided by 125 into 10 raised to minus 6. That will give us 1.544 into 10 raised to 6, or simply 1.544 megabit per second. Or simply the bit rate of T1 carrier system is 1.544 bits per second, megabits per second. 1.544 megabits per second. It's not shown here. One more thing. So what will be the bandwidth required for T1 carrier system? So minimum bandwidth is nothing but half the bit rate. So bit rate is 1.544 megabit per second. So the bandwidth required for T1 carrier system is half of 1.544 into 10 raised to 6, which will give 772 kilohertz. So minimum bandwidth of T1 carrier system is 772 kilohertz. Once again we'll see T1 carrier system. In T1 carrier system, it will have a 24 channel which is multiplexed by time division multiplexing, and each channel is band limited to 3.3 kilohertz, and we are using 8000 sample per second, and we are using 8 bit per sample, so which will give 24 into 8, so 192 bit will be the output of this coder. And one more bit we are adding for the frame synchronization, that is called f bit. So for every frame which consists of uh, 24 samples or 192 bit, one we are adding one more bit, that is f bit, that is frame synchronization bit. Framing bit or frame synchronization bit will be added, so it will makes 193 bits. Now 193 bits are transmitted in 125 microsecond, so total number of bits in 1 seconds are 193 divided by 125 into 10 raised to minus 6, which will give 1.544 megahertz or megabits per second. Thank you very much. This is our end of our chapter.